Alright, we are recording and take you to the practice quiz. Problem number 1. Write the coordinates of each red dot. Place the coordinates next to the red dots. Now this is a unit circle, so the center of this is at the origin of the XY coordinate system, and the radius is 1. So let me give you a moment to write the coordinates of each of those 4 red dots and write them right next to you. So you might have to, draw all this on your own sheet of paper. Take 30 seconds more. Oops. So if this is the x-axis, this is the y-axis, and it's 1 unit is the radius, then this must be 1, 0. This must be 0, 1. This must be negative 1, 0. This must be 0 over 1 down. Now I could imagine, if I was in your shoes, I'd have gotten really confused by these directions, and I might not have done this. Give me a little feedback. Did you interpret it this way when I asked you to write the coordinates of each of these points? Okay. It's understanding what was asked of me, which was often the hardest part. What did you really mean? And then, from the picture above, find the sine of 90 degrees. Okay, 10 more seconds. All right, sine of 90 degrees. Let me just review something real quick. If I have an angle on a unit circle, so this is 1. Here's a unit circle going around. This is x, this is y. The cosine of this angle theta, come on, if I write small it tries to interpret something else. The cosine of theta, we know from SOHCAHTOA, ka, cosine is adjacent of the hypotenuse, x over 1. The cosine of the angle is the same as the x-coordinate of this point. If I was able to write the x and the y coordinates of this point, but I was able to do that up here and over here. If I was able to write the x and y coordinates, the x coordinate I wrote is the cosine of that angle. And the y coordinate is the sine of that angle. So here is the 90 degree angle. Theta is now 90 degrees. The sine of theta is the y coordinate of that point. So it is 1. So the sine of theta is equal to 1. Now, give me feedback. Were you able to come up with that answer? Because that tells me something about how much more I need to review this or not. Were you able to come up with 1 before I gave it to you? So that feedback's pretty important here. Because it's when I got lost on some of these fundamental steps is when I really got lost in math. Okay, so do the cosine of 180 degrees. Now these we're going to go quick. And I'm not even going to tell you when time's almost up. Alright, 180 degrees is over here. The cosine is the x coordinate, so it's -1. Do the next one. Sine of 270 degrees. Okay, the sine is the y coordinate. So 90, 180, 270 is down here. And so it's the y coordinate, so it's -1. And do the next one. Cosine of 0 degrees. Zero degrees is up here, and the cosine then is the x coordinate, which is 1. And give me feedback on all of those. Are you feeling really comfortable with this? Or is it still kind of a bit fuzzy? Okay, not everybody's going to be totally comfortable, I'm pretty sure. But this one takes a bit. Okay, 1, 2, 3, 4, 5 feedbacks. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 people here. Could I get feedback from everybody in here on these things? Okay. And, alright, do this one as well. Cosine of pi over 2. Alright, and pi over 2 is the same as the 90 degree angle. The cosine is the x coordinate of that point, which is 0. So if I scroll up and look at it, it's a 0 line up. Alright, place a blue dot on, I'm going to do a blue dot. You can probably don't have colored pens, but on the unit circle above, and write the coordinates of the dot at 45 degrees. Alright, so placing a blue dot here, 45 degree angle, and then we're writing the coordinates of that point. Give you 10 more seconds. The coordinates are square root of 2. I'm going to have to zoom in a little bit so I can write it a little bigger. Square root of 2 over 2. Square root of 2 over 2. Now, how did we know that it was going to be square root of 2 over 2, square root of 2 over 2? Yesterday, we were kind of going kind of fast. It was towards the end of class. We did this thing with the 45, 45, 90 degree triangle. And by just drawing one 45, 45, now that's called an isosceles triangle. These two sides had to be equal. When the angles are equal, the sides are also equal. And we said, let's make this one be 1. And then these two can be the same letter, because they have to be equal. And then we just solved x squared plus x squared equals 1, and we wound up getting x being square root of 2 over 2. Now, if x is square root of 2 over 2, then the cosine of 45 degrees is the adjacent over the hypotenuse, square root of 2 over 2 over 1, square root of 2 over 2. So this square root of 2 over 2 twice. All right, give me feedback. Were you able to get the square root of 2 over 2, square root of 2 over 2 before I put it up there? Alright, and then the only other possible coordinates on the unit circle besides 0 and 1, 0 and plus or minus 1. 0 and plus and minus 1 happens at those red dots. All the other places on this unit circle, key points on the unit circle, they don't use 1 or 0. They only use 3 possible numbers, square root of 2 over 2, or 1/2, or square root of 3 over 2. Now, square root of 3 over 2, you can see, is bigger than 1/2. It's almost 1. 1/2 is the same as 0.5. We're going to place a green dot on the 30-degree angle at the unit circle, and then draw the triangle inside the unit circle at that point. So see if you can do that. Green dot. What do I mean by draw the right triangle inside the circle? Let me come over here and let me get rid of this. Here's the 30-degree angle. Now the right triangle inside the unit circle is like comes straight down. There we go. And this is the 30-degree angle. Alright. So, now notice, over looks like it's more than up. When you're at a 45-degree angle, you go over and up the same amount. But this one, it looks like we go over further and then up smaller. Alright. Since the two coordinates of this point are 1/2 and square root of 3, which of these is on the longer side of the right triangle? Label the two sides of the right triangle we just made with those two values, either 1/2 or square root of 3 over 2. Let me give you a moment for that. All right, since the longer side, it's got to go with the bigger number. We see square root of 3 over 2 significantly bigger than 1/2. That's got to be this one. And this one is the shorter distance, so it's got to be the 1/2. Now, when I write down the sides of this triangle, I'm also giving the coordinates of this point. You go over square root of 3 over 2 and up 1/2. All right. Now, got that down. So go to, I have this renumbered at 1. So find all trig functions of pi over 6. So there's 6 different trig functions. Find them all of pi over 6. 30 seconds more. So, when we write these down, I always write the cosine first. Why do I always write the cosine first? Because it's the x-coordinate. And we write x-coordinates before y-coordinates. Sine is the y-coordinates. But strangely enough, most textbooks, when they're writing all six, will usually start with sine and then they'll do the cosine. I don't understand why they tend to do that. So the cosine of pi over 6 is just the x-coordinate of this point right here. Square root of 3 over 2. And the sine of pi over 6 is 1/2. The only time square root of 2 over 2 ever shows up is when you're on a multiple of, it's one of these 45 that's halfway between these red dots. All these 45 halfway between the red dots. That's the only time you ever see that. And it's the same amount over as up, and that's why they're both the same. The other two show up on all the other ones. And so we have this, and then the reciprocal of cosine is cosecant. No, can't start with the same letter. It's secant. That's the same as this, but flipped over. So it's 2 over square root of 3. And secant and cosecant, as long as I don't start with the same letter, I have the reciprocal of it. Flip the 1/2 over and you get 2. And then we have tangent and cotangent. Now, on the sine level, I'm going to put the tangent. Why do I put it over there? Tangent of anything is sine over cosine. So the sine I think of as the dominant part of this because it goes on the top. So I kind of associate tangent with sine. And so it's going to be this 1/2 divided by this one over here. So 1/2 over this one, square root of 3 over 2. Now, SOHCAHTOA. No, screw that. SOHCAHTOA. Notice sine goes with opposite. Cosine goes with adjacent. TOA doesn't have the hypotenuse. They cancel each other out. But it's the sine's symbol over the cosine's symbol. So you can even get this, that tangent is sine over cosine from looking at SOHCAHTOA. Now, this is 1/2 times copy dot flip. And the 2's cancel out. I get this. Now, once I get the tangent, I could do the cotangent. I could do the cotangent by cosine over sine, but the fastest is just take whatever you got for tangent and flip it over. Square root of 3 over 1. And there's the 6 trig functions of pi over 6. Now give me feedback on this problem. All the trig functions of pi over 6. This area of trig is, if I lose you here, it's hard to recover you because we'll assume this and then we'll race forward. But in the past, I've had students who have gotten stuck right around here. And that's why I'm really, really interested in your feedback here. Okay, I'm seeing an honest response, a little confused. Thank you, Sasha. Need review on the tangent. Need to practice it. And Sasha, feel free to give any more input, like specifically if you're confused on a specific topic, please ask.
Like I get like the cos and sine. I just don't get where you get the like. I get the point, like the points. You know, like where the square root of 3/2 and then the 1/2. That's the part when I'm confused. Like where it's like the angle of 30, I believe. Like that point, like the points.
Okay.
That's the because I get where you got like the cos and everything like that, but that's the where I'm confused.
Okay. Let me go over a couple things. I'm not sure if this will go to where you're confused, but I'll check in with you in a minute. All right,
Okay.
so on the unit circle, let's go back. We were looking at the 45, 45, 90-degree triangle. The 60-degree, 30-degree, that we started with this black triangle, just this one right here. And I put a mirror image of it right below it. And so it made it 60, 60, 60 all the way around. And then I said, all right, let's let this one be 1. You can make it to be 100 or 1, it doesn't matter, because it's the ratios of these things. As long as it's a similar triangle, it'll work. So I could let anything to be 1. But notice that this one is exactly the same as this one, because it's the mirror image of it. And this outer one is now a 60, 60, 60. It's what we call an equilateral triangle. So all three sides, if all three angles are equal, all three sides will also be equal. So they're all of length 2. So that's 1, that's 2, and then now that tells you right away that this angle right here, if I took opposite over the hypotenuse, that's the sine of 30 degrees. I get the opposite, which is 1, over the hypotenuse, which is 2, and that's the sine of 30 degrees. And then in a similar way, I did this. Well, first of all, I did the Pythagorean theorem, and I came up with this had to be the square root of 3, and then I could then take the cosine, or the cosine of 30 degrees turned out to be square root of 3 over 2. So that's where I first came up with these numbers, 1/2 and square root of 3 over 2. But when we're putting them together inside a unit circle, the way we remember them easily is if I'm on a 45-degree angle line, which do I go over? Which is bigger, going over or going up? Well, they're equal, and that's what keeps you on a 45-degree angle line. So these two numbers had to be equal to each other. And that'll always use up between the three values, 1/2, square root of 2 over 2, square root of 3 over 2. This one always gets used up only on the 45. The other two always go together. And the only then difficulty, now we know that the red dots all have those coordinates. The blue dots are at the 45-degree angles, halfway between the red dots, and those will only use the square root of 2 over 2's. All the other ones are going to be green dots. All these green dots can only use the numbers 1/2 or square root of 3 over 2. But it's a really big issue. How do I decide which one? Is it square root of 3 over 2, or is it 1/2? Well, you draw the triangle. Like, for instance, this one right here. Now you ask yourself, which is bigger, the over or the up? Well, on the 45-degree angle, they're equal. On this side of it, it's more up. On this side of it, it's more over. So this is the bigger one, and it's going to be negative because you're going to the left. So I'm going to go left 1/2, or negative 1/2, and then I'm going to go up the larger because the up is bigger than the sideways. Square root of 3 over 2. Now, Sasha, I might or might not have gotten into what was confusing you. Did it? Did that?
Yeah, it was because when I was watching the videos, when 'cause I wasn't here last class, when I was watching it, I didn't quite get it. But now that you explained, it, I understand.
Okay, good, good. And that also explains a bit of your confusion. Yeah, if you missed that class, that would be tough. Yeah. All right. So, all right, let's go to the next. All right. Place a blue dot. Oh, we already did that. We already did that. All right. So, on the interior, we're going to do a little bit different activity with the unit circle now. On the interior of the circle, label each angle in radians for quadrant 4. Now, quadrant 4 is down here. This. So on the inside, each angle, and we were putting degrees on the inside, now we're putting just radians on the inside. On the exterior of the circle, label the x and y coordinate of each point where the angle and the unit circle meet. So you're going to label each of these points here, 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 and here. All those in quadrant 4. Note this also represents the cosine and the sine of the angles. So let me give you a little bit of time to complete this task. Thirty seconds more. All right, so this is 0. This is pi, 3 pi over 2. And then this is 1 pi over 4 this is negative pi over 4. But instead of negative pi over 4, let's think of this for a moment. This is 2 pi, but it's also 8 pi over 4. If you go backwards 1, it's 7 pi over 4. Now, if this is pi over 6, this is negative pi over 6. As long as I double that denominator, that's the same as 2 pi. 2 pi minus 1 pi over 6 is 11 pi over 6. And then this up here is pi over 3. So if I had a 3 down here, this would be 6 pi over 3. And then subtract one of those, because that's the same as negative pi over 3. This is 5 pi over 3 for that one. All right, and then the coordinates. So let me take this point. I go 1 over 0 up. This one. Well, let's do this one. Let's do the easy ones first. 0 to the right, 1 down. And then this one, I'm going to go square root of 2 over 2 to the right, and then I'm going to go that same amount down. So, I told you that square root of 2 over 2 were the only ones that showed up on all the blue dots. But the only thing that changes is pluses and minuses to move you to the right quadrants. Okay, I went to the right and then down. And then over here. Now the only two numbers left over are 1/2 and square root of 3 over 2. But I got to make sure I don't mix these up. Well, look at, I go more to the right, and then I go down less. So the bigger number has to be the x-coordinate, smaller number the y-coordinate. And then this one, it's reversed. If I made the right triangle from here, smaller one over, the bigger one down. Oh, but I have to make the down negative. Okay. So over is positive, and then down the larger one, right here. Okay, so give me feedback on this. Is this overwhelming? Too much information? Or feeling like, hey, with a little practice, I think I can get this? Okay, now, the unit circle. That thing is in the homework as a worksheet. And I think it was in, like, 7.3 or something like that in the homework. So practice this. One way to practice it is to complete an entire unit circle like this. It's really good practice with all those radian angles, putting those on the inside. After a while, you might be comfortable enough with the degree angles, you don't need to include those anymore. So but getting all the radian angles, and then after a while you'll even start to get them kind of memorized. Oh yeah, 11 pi over 6 very quickly is way over here. You might have to do the mental math for a while to get it, but after you do it a little kind of some repetition, these angles, we're going to be doing this so often, you want to have really quick visual representations of all this kind of stuff. And then be filling in on the exterior of the circle all of these coordinates. Okay, now, before we go on, let me put a couple extra problems up. Find the cosine of 5 pi over 3. Find the sine of 11 pi over 6. Don't use a calculator, don't look up in a textbook or anything, just look at the picture. Write these values down. Okay, cosine of 5 pi over 3, I just look at, oh, here's the angle right here. Cosine is the x-coordinate. The sine of 11 pi over 6, here's the angle, 11 pi over 6. The sine is the y-coordinate. All right, now, are you going to be expected to memorize these kind of things? Yes. Now, you don't memorize it by trying to commit all these different things to memory. You way overload your memory system. Nobody can memorize, that I know of, can memorize 11 pi, sine of 11 pi over 5 pi over 6 is negative 1/2. But we can reconstruct it with the unit circle. When I have to do sine of 11 pi over 6, how I do it is I make a tiny little unit circle and I go around a full 2 pi, and then I say, oh, now that would be 12 pi over 6. I'm going to come back 1 pi over 6, which is the same as 30 degrees, and I'm going to get right here 11 pi over 6. So I can kind of visualize it right there. Now then I say the sine of that, that's the y-coordinate. And I know it's got to be either 1/2 or square root of 3 over 2, positive or negative. And I can answer both of those questions by just looking at this picture. Well, it's the height, which is smaller than the over, so it's 1/2. And then it's down, so it's negative. And so this tiny little picture would enable me to have this. So we say that we've memorized these values, but we've really understood the unit circle so that you don't have to memorize all the values. But you've got to be able to come up with all these kind of answers exactly from the unit circle. Okay. And a number of people gave feedback that with practice, they feel like they're going to understand it, but they need more practice. And I would fully agree. You just need to keep working at it. You're going to get some of the practice because a lot of these problems are going to keep asking these questions. But you may need to just write out your unit circle a number of times on your own, and that could do it. It can help you a lot. Okay, let's go to number 3. Write the main Pythagorean identity. Show its relationship to the triangle below. So don't look this up. We gave it last time, the main Pythagorean identity. Do you remember what that is? "20 seconds. Alright, the main Pythagorean identity is cosine squared. Now it can be any angle you want. You could put t, theta. So oftentimes we use Greek letters for the angles. Plus sine squared. It's got to be exactly the same angle whenever you use that. And then it's going to be 1. Okay? And then, now that we have the main Pythagorean identity, show its relationship to this triangle over here. I did something like that, and let me start you with that. If this was theta, it can be anything you want as long as these two agree. If this was theta, look at the picture and think of SOHCAHTOA. From the picture to write the ratios over there. And let me give you a minute. Alright, so on this picture, the Pythagorean theorem, which is different than Pythagorean identity, Pythagorean theorem tells us that x squared plus y squared is the same as r squared. Now, cosine theta, let's look at this picture. Cosine theta is adjacent over the hypotenuse, x over r. And sine theta is opposite over hypotenuse, y over r. So this is telling me cosine squared theta is x over r squared. Sine theta is y over r. Is 1. Now, let's square this out. It's all one term in here. So I can distribute the exponent to both parts of the fraction. And they have common denominators. If the denominators are the same, I can add the numerators. But x squared plus y squared by the Pythagorean theorem is the same as r squared. Does r squared divided by r squared equal 1? Yeah, anything divided by itself is 1. Show its relationship to the triangle. Now you could make an argument kind of in reverse. You'd say, look, do you agree that r squared over r squared is 1? Yep. And if you argue up this way, well then, r squared is the same as x squared plus y squared, which is the same as this, which is the same as this, which is the same as this, and we see that we will arrive at the Pythagorean identity. Pythagorean identity, if somebody agrees that r squared over r squared is equal to 1, they're also agreeing that cosine squared of theta plus sine squared theta is equal to 1. All right. Give me a little feedback on number 3. Is this making sense or is this confusing you? Thank you. All right, so we are at a break time, so we will start again. And before I take my break, anybody need to speak with me? Okay, let's start up again. And we have two more practice quiz problems. Convert to degrees both times with pi over 6 and 1 radian. And let me give you a quick minute on these two. Thirty seconds more. All right, on convert pi over 6 to degrees, we could just kind of look and say, all right, there was 30 degrees right over here. And that's the same as, I know that I've memorized that, that's pi over 6. So you could just do it from memory and say it's 30 degrees. And that would be fine. You could also do it. Now, when you don't see a unit, we assume RAD. Our radians are actually unitless, so you don't have to write the units. And then we multiply by a conversion factor. We want to get rid of radians, and we want to turn it into degrees. We could go through 2 pi and 360, or 1 pi and 180. And the pi's would cancel. The radians would cancel. 6 goes into this 30 times. 30 degrees. And we'd get the same thing if we did it. Now, 1 radian is super important to us. In fact, whenever you learn a new unit, you always need to find out what 1 of that unit represents and have it as a baseline. So 1 radian, we're not used to radians except when they're in terms of pi. But they don't have to be in terms of pi. They can be just numbers. In fact, if somebody tells you pi radians, they could have told you 3.14 radians. And that's almost exactly the same thing, just a tiny, tiny bit off. Okay? So 1 radian, oh, and I'll put this equal sign here. I multiply, I want to get rid of radians, and I want degrees. And so pi radians, 180 degrees. And then this, the radians cancel, and I get 180 over pi degrees. Now, 180, if I punch this out of my calculator, pi is around 3, so I'm going to get around 60. But 180 divided by pi, more precisely, would be 57.3, around 57.3 degrees. Now, it's very close to 60 degrees. And that makes sense if we look back over here. If this is pi, way over here, pi radians, pi is 3.14. So 1/3 of that is like 1/3 the way around the circle. 2/3, 3/3. So very close to 60 degrees is 1 radian, 2, 3 radians, etc. All right. And let's go to the next section. Oh, before I go to the next section, any questions on homework problems? We don't have a lot of time for questions on homework problems, but I can, if they're kind of quick, I can go over them. If they're really long, I might have to delay till next time. Questions?
Mr. Shankin?
Yes.
I had a question on number 101
Okay.
at the end of 7.3.
All right. 7.3. What are the coordinates of the child after 90 seconds? Alright. And oh, 637. Alright. So this says, a child enters a carousel that takes 1 minute to revolve around once. The child enters at the point, so I'm going to draw this as if it was a unit circle. The child enters at the point 0, 1. 0 over 1 up, right up here. That is at the due north position. Assume that the carousel revolves counterclockwise. So the carousel is going to revolve in this direction. It's an arrow. Okay. What are the coordinates of the child? Alright. Takes 1 minute. So at t equals 0, it's going to be right here. And it's also going to be right here at t equals 60 seconds. Because in 1 minute, it's right back to where it started. And then, what are the coordinates of the child after 90 seconds? Well, if it's 0 seconds, all the way around, 60 seconds is back here, then halfway would have been 30 seconds. So 30 seconds, 60 seconds, it would have also been 90 seconds back down here again. So what are the coordinates of the child? Would be 0 over negative 1 down. That's my answer. Does that answer your question?
Yes, thank you.
Who was that?
This was Brianna.
Brianna. Thanks for the question, Brianna. Glad that answered it. Any other questions?
Mr. Shankin, I also have another one.
Mm-hmm.
I struggled with the review in the beginning, and I think it's how to position the triangle.
Okay.
It's basically what you went over in the beginning.
So what page and what number? Is that from?
It is
Okay.
page 637. Wait, I'm sorry.
Or what section? Either way.
I'm sorry. It's 7.3, page 637, number 22.
637. Okay, same page that I'm on. Is it this one right here? Sign of 2? Or sign of 0?
637. No, it's.
This is 7.3.
I'm sorry, it's the wrong page.
All right. Hey, why don't I go on with this, and then at the end, let's go back, and I'll come back to you. Okay?
Okay, thank you.
You're welcome. All right. So let's go 7.4, the other trig functions. All right. Problem 1. The sine of alpha is negative 2/3. And alpha is in quadrant 4. So let me draw a quick little picture. I'm going to have a unit circle. Now, the sine of it is the same as the y-coordinate. So, the y-coordinate being negative 2/3. So here's about half, a little bit more than half is negative 2/3. The y-coordinate is negative 2/3. Now there's two possibilities for this angle. This angle could be over here, or it could be over here. And they said that it's in quadrant 4 to differentiate those two, to tell you that it's this angle right here. If they didn't tell you quadrant 4, it could have been over here, because that also has the y-coordinate. Remember, the sine is the same as the y-coordinate. So here's the angle alpha. Now, the angle alpha, I really should draw it over here. But we often don't. We often draw the reference angle. The reference angle is way easier to work with. And so sometimes we even label that alpha. And it's not really exactly alpha, but it's the reference angle. Remember, the definition of the reference angle is the shortest possible, smallest possible angle you can make with either side of the x-axis. And it makes it really, really quick and easy to work with. All right. So we have this. We're going to find all the other trig functions of alpha by drawing the reference angle and the right triangle. Now, when it says draw the right triangle, it just means from this point, come across, we got this right triangle. So I'm going to blow up that right triangle, take it out of that picture, and I'm going to get it like this. And even though this isn't really alpha, I'm going to put alpha here. Let's see. Oops. The reference angle for alpha. So that triangle is blown up over here. And now, these two distances, the sine of any angle is from SOHCAHTOA, opposite over the hypotenuse. Now, so this is really the opposite. That's the hypotenuse. So let's make the 3 over here and the 2 be opposite of this, like this. So it's kind of like putting the 3 over here and the 2 over here. Now, you might say, hey, you didn't use the negative. If you go over to the right, you got to go down 3. This should really be negative 2, not positive 2. Well, we make everything positive. We just make everything super simple in a reference angle. We simplify the angle so that it's a reference angle. We make all the numbers positive, and then we can get the negatives later on that we need to from the side, taking into account what quadrant we're in. All right. So, if I could just find this right over here, let's call it W for a minute. If I could find W, then I could get all my trig functions, because SOHCAHTOA, adjacent over the hypotenuse, tangent opposite over adjacent, and then I got everything. I just flip them over to get to all the others. All right, so all I need to do to get W is use Pythagorean theorem. W squared plus 2 squared is 3 squared. W squared plus 4 is 9. Subtract 4 on both sides. W squared is equal to 5. Square root both sides. Now when you square root both sides of an equation, you're supposed to put plus or minus. But we're just making it really simple. Everything's going to be positive. Alright, so now we're going to go by, before I do this next part, let me just point out, when we were over here in quadrant 4, x coordinates were positive, the y coordinates were negative, because you go to the right and down. In quadrant 1, you go to the right and up, so positive, positive. Here you go left, which is negative, and up. Here you go left and down. Here you're going to get negative, negative coordinates. So we can tell whether they're supposed to be positive or negative by just looking at what quadrant we're in. All right. So once we have these things, we have this triangle, we can come up with cosine of alpha, sine of alpha, and then all the other things as well. Sine of alpha was already given to us. And alpha, by the way, is the first letter of the Greek alphabet. Alpha, beta, gamma. The cosine is the adjacent, so katoa, over the hypotenuse. So square root of 5 over 3. But before I put in any of these things, let's do this. Let's figure out what the sines of all these are going to be. Is cosine of a quadrant 4 angle going to be positive or negative? It's going to be positive because you go to the right. Now, we're going to also be finding out, I'll just kind of separate this. We have cosine, we're going to have secant. Now, since the secant is the same thing as this, but you just flip it over, it's also going to be positive. You're going to have cosecant, which is the same as this, but just reciprocated. And when you reciprocate a negative number, you get a negative number. You're going to get tangent. I like to put that on the line of this one. Tangent of alpha. Now, tangent is the sine over the cosine. But a negative divided by a positive will be negative. And then the cotangent is the reciprocal of the tangent, and that doesn't change its sign. So we figured out the sines of all the numbers first. So the cosine is adjacent over the hypotenuse. Secant is whatever this was flipped over. Cosecant is whatever this was flipped over. Tangent is sine over the cosine. Now, a fast way to do this is they're both going to have the same denominator because they both have the hypotenuse. That winds up going away, get canceled out. It's this divided by this with copy dot flip. But you're going to wind up getting the top of the sine over the top of the cosine. The denominators are going to wind up canceling out because you flip this one and then multiply. Okay, we had already determined that it was negative, and then cotangent is the same as tangent, but flipped over we have all this. All right. Everybody okay with all of this? All right. If there's no questions, then let's go to the, so that's how you get all the trig functions. If you're given one of the trig functions of an angle, you're really given all the trig functions of an angle, but you need to know what quadrant you're in. Okay. The other Pythagorean identities. Well, we had this one in the practice quiz. Pythagorean, the main Pythagorean identity. Cosine squared plus sine squared is equal to 1. Well, there's two others. Let's go over them. All right, so the first one is cosine squared theta plus sine squared theta is equal to 1. What I'm going to do is, this is the main Pythagorean, identity. We find the other ones by divide both sides by cosine squared theta. So I'm going to take the same one and I'm going to divide both sides by cosine squared theta. When you divide the right side, there's just one term, and so you just put cosine squared theta. When you divide, when it's more than one term, every single term has to be divided by it. Alright, now let's simplify this. Anything divided by itself is 1. Sine over cosine could also have been written like this, because that squared would just distribute to both. 1 over cosine squared is the same as 1 over cosine squared, because 1 squared is still 1, cosine squared. So I'm going to just change the order slightly on this now. Sine over cosine is the same as tangent. Tangent squared theta plus 1 equals, when you reciprocate this, you can't start with the same letter, secant squared theta. This is one of the other ones. There's another one besides this, and you're going to need to wind up memorizing this formula. Alright, so just like you need to memorize this one, it's the main Pythagorean identity, you're going to wind up memorizing this one. Tangent squared and secant squared have this relationship. Okay. And to find the other Pythagorean identity, we change color. Green. We're going to divide both sides of the original equation by, not by sine squared, but not by cosine squared, but by sine squared. So we're going to start with the same cosine squared plus sine squared equals 1. Now, when I say them out loud, I often don't say the angle. I say cosine squared plus sine squared equals 1. But when I write them out, you have to have an angle right after that. Trig function without an angle doesn't mean anything. Okay, and then I'm going to take this, I'm going to divide both sides by sine squared. Okay, now this becomes just 1. Cosine over sine is cotangent. 1 over sine squared is 1 over sine is cosecant, so this is cosecant squared. This is the other one. Tangent and secant are related like this. Cotangent, cosecant are related. And since you have to have these memorized, I'll tell you a little trick that I used to have really a hard time. I got used to tangent and secant being together, but I couldn't remember, does the one add to this side or does it add to the other side? If you get it on the wrong side, it doesn't work. And then finally I realized what worked for me, might not work for you, was tangent is a lot more complicated than secant. Secant is just 1 over cosine. Tangent is sine over cosine. It has both of those trig functions in it. All right. So you add 1 to the more complicated one, and it simplifies down to the less complicated one over here. And that helped me remember it. And so these are the 3 Pythagorean identities that we're going to have to commit to memory. The main Pythagorean identities. All right, now, what are these Pythagorean identities useful for? All right, we're going to do the same problem that we just did. If the sine of theta is negative 2/3 and alpha is in quadrant 4, find all the others. Same problem. Find all the other things, but this time we're going to use Pythagorean identities. It's an algebraic way to do these problems. And we don't have to draw any pictures to do this. So I can get all the other trig functions from this one by, now in fact all I really need is the cosine. Once I get the cosine of alpha, if I have the sine and the cosine, all the others can be found by just making fractions of those things. All right. So really the first step is find the cosine. So I'll put find cosine of alpha. Now how did we find the cosine of alpha earlier? We drew a picture of the right triangle. And then we found with the Pythagorean theorem this leg and then adjacent over the hypotenuse. Well, we won't need to do that anymore. We'll find the cosine of alpha by using one of these 3 Pythagorean identities. Now, we know sine and we're trying to find cosine, so we want the first one. If we knew tangent and we were trying, or secant, and we were trying to find tangent, or vice versa, and knew one of these and wanted to find the other, use this next one. If you knew one of these 2 and need to find the other, use this one. So use one of the Pythagorean identities, one of the 3 that you need, by using cosine squared angle plus sine squared, as long as it's the same angle, equals 1. Now, how does this get me the cosine? Well, this, what does cosine squared alpha really mean? It really means this. Sine squared alpha really means this. This negative 2/3 is the same as sine of alpha, so it's going to go in right here. So I'll go back to the normal notation. And now I'm going to square that out. And I'm going to make 1 over 1 into 9/9. And then I'm going to subtract 4/9. We have common denominators now. And a little more space. So I'm going to get cosine squared alpha. 9/9 minus 4/9 is 5/9. Then I'm going to take the square root of both sides. When I do that, I insert a plus or a minus sign. Now, this plus or minus sign, we have to figure out. Now, sometimes it means both are solutions, but not in this case. In this case, it means one of those is right, plus or minus, and one of them is wrong. Figure it out. Well, they told us that alpha is in quadrant 4. So my little mini picture is I know I'm down here. And that means you go down, so that's why the sign is negative, but you go to the right first, and so that's positive. The cosine is going to be positive. All right, so we're going to choose plus, because alpha in quadrant 4. You know, you go over to the right, and so then we're going to get, now I'm going to put a separate square root on the top, separate square root on the bottom. The bottom square root of 9 is 3. All right. Thus, cosine alpha sine alpha. And we do exactly what we did before. We transfer this right there. We do this. Bring it down. Put it here. And then you can get all the other trig functions. But notice we'd get square root of 5 over 3. What had we gotten before? Square root of 5 over 3. Negative 2. We'd get exactly the same values. What these Pythagorean identities allow us to do is be an algebraic person instead of always having to be drawing right triangles. They have other applications as well. So if you decide, hey, I just as well use the right triangle, you still need to learn these Pythagorean identities. They're very useful, and they'll come in handy in other times as well. All right. I covered a lot of material. Give me a little bit of feedback here. Need some more review with this, or are you good with this? Three Pythagorean identities, how they can be used. Need more review. Need more review. It's good feedback. More review. It's a lot of material. Okay. Alright, so I'll make sure that I include some more review. You all are pretty clear on that. Okay. Alright. Let's go through negative angle identities, a couple things, and then I think I'll probably have to put the review into the practice quiz next time, because we've got a couple more things to get through very quickly. Negative angle identities. And alright, because of time considerations here, let me go through a really quick idea. If I was to find the cosine of pi over 6, and I was to find the cosine of negative pi over 6, let me give you the visual representations of those. So, here's my unit circle. Here is pi over 6. Here is, you start the same place, but you rotate the opposite direction, negative pi over 6. So whether I land on this green dot or on this blue dot, the cosine is asking, what is the x-coordinate of the pi over 6? Now the x-coordinate of this point and the x-coordinate of this point are the same, because you go over the same amount. So pi over 6, now remember it's going to be one of these two numbers, either 1/2 or square root of 3 over 2. Well, when you're at pi over 6, do you go over further or up further? You go over further, so pick the bigger number, square root of 3 over 2. And the cosine of negative pi over 6, the cosine of negative pi over 6 down here is the same thing, because you're going over the same amount. Alright, so down here it asks us, circle the true statement. Cosine of negative t equals cosine t, or cosine of negative t equals negative cosine of t. What it's saying is, do these two things give you exactly the same, or do they give you things that are opposite? And these two things did not give us things with different signs, so I don't pick this one. I pick this one. I get the same thing whether I take the cosine of a positive angle or a negative angle. I'm always going to get the same thing. And if we had time, we would experiment with our calculators. You might do that after class, is, put various angles in. Cosine of 30 degrees, cosine of negative 30 degrees. You get the same answer. All right. Now, it's not that case, though, with the sine. Let's look at the sine. The sine of pi over 6 and the sine of negative pi over 6. They're the same two locations, the green dot and the red dot. But the sine is the y-coordinate. To get to this one, you have to go up. So a positive y-coordinate is the smaller of the two amounts, so it's 1/2. But the sine of negative pi over 6, you go down. And you get negative 1/2. Now, this is certainly looks logical since it's a quadrant 1 angle. But even if I had quadrant 2 angles, or any quadrant angles, let me just show you real quickly in a quadrant 2 angle. If this was my angle that I was looking at, versus the negative of that angle, one's going to be up, one's going to be down. They're going to be the same distance over, but one will go, you have to go up, and the other you have to go down. So, for the sine, it turns out these two things are not equal. But these two this is saying that they'll have opposite signs. There's an extra negative sign with one of them that you have to have in order to make them equal. Okay. And then from those you can determine all the other trig identities for the negative angle identities. Secant of negative t is the same as 1 over the cosine of negative t. But the cosine of negative t is the same as the cosine of t from up here. And this is the same as the secant of t. So secant works just like cosine does. They have the same sign. But cosecant is going to be opposite, and so on. And you can work the other ones out. And the homework is 7.4. And we will stop here. And Brianna, I didn't get time to get to your question. We'll do that at the beginning of class, or when I get to questions next time that we meet. And anybody else have any questions or comments before we go? And reminder that we've got one more class on Thursday, on Thursday, and then we have spring break. We'll come back from spring break. On that Thursday is exam 2. And so you should be working on the exam 2 practice test. And on Tuesday after spring break, that's when that exam 2 practice test is due. And then you make corrections on that and turn that in before the exam. All right. We'll stop here. I'll see you all next time. Unless anybody needs to talk to me individually.
Bye. Thank you.
You're welcome.